Okay, now we're moving on to stocking density. Now, this is where we start to get into a little bit of the math. I want all of my non-math people to not freak out. Just go ahead, listen to what we're teaching, try to work out the problems, because you really just need to take out the numbers that I've put in and put in your own numbers and perform the calculation. So it's as easy as that. Use what I've put up here as a template, draw it out on paper, and practice, because you're not going to do it once and just know all these equations. It takes practice to become familiar with them. So in saying that, we'll go ahead and start. The first formula here is D density equals L over C density, where D density is in kilograms per cubic meter and L is the length of the fish in centimeters. Now, for all my people using US standards, you can use pounds per cubic foot in inches instead of the kilograms per cubic meter and centimeters. You will also notice that throughout the rest of the course, I try to put US standards and metrics up so that everybody from the US can understand everything and everybody in the rest of the world can understand everything. C density equals, for tilapia, 0.24, for trout, 0.32, and for hybrid striped bass, 0.45. And that's using the metric, if you're going to use kilograms and centimeters. C density for tilapia is 1.5, for trout it's 2.0, and for hybrid striped bass it's 2.8 if you're using the US standards, the pounds per cubic foot in the inches. Safe maximum stocking densities for experienced aquaculturists using properly engineered life support equipment and oxygenation is going to be 1.05 pounds per gallon, which is 126 kilograms per cubic meter. And for trout, it's going to be 0.91 pounds per gallon, about 110 kilograms per cubic meter. Beginners, again, should target half of these values. Don't try to do the maximum that 20-year veterans are able to achieve. Start low and work your way up. Tilapia, again, 0.5 pounds per gallon, which is roughly half of what we had just said for oxygenation. And for trout, 0.45 pounds per gallon. Minimum water velocities must be maintained in order for proper tank hydraulics and self-cleaning characteristics to actually work. Optimum velocities are going to be between 15 and 30 centimeters per second. Safe swimming velocities for fish are between 0.5 and 2.2 body lengths per second, and that depends on how old the fish is. Body length times the safe swimming velocity in body lengths per second equals the proper tank velocity. So the proper tank velocity within the tank, how fast you're spinning that water. The equation to solve safe swimming velocity is Vs equals 5.25 divided by L to the 0.37 power. Okay? It's actually a very easy equation. Vs is the body length per second, maybe 2 body lengths per second. Okay? L is the length of fish in centimeters. Very easy. So let's do 3 different examples. The fish body length of 10 centimeters, 20 centimeters, and 30 centimeters. Now, of course, these would be 3 different tanks. These wouldn't all be swimming around within the same culture tank. For 10 centimeters, we have 10 to the 0.37 equals 2.34. 5.25 divided by 2.34 equals 2.2 body lengths per second. Pretty easy. 20, we're going to move on to the 20 centimeter. So 20 to the 0.37 is 3.03. 5.25, which is a constant, divided by 3.03 equals 1.7 body lengths per second. And then for 30, we do the same math. We get 3.52. 5.25 divided by 3.52 equals 1.5 body lengths per second. Now, this is exactly what you need to do to get comfortable with these formulas. Go in here and do 5, 12, 15, 20, 22, 24. It takes repetition before it actually is going to stick into your brain. So this is one of the easier formulas that we're going to go through, but right there you've figured out what velocity you need to spin the water in that tank for proper growth and health for those fish. So back to the main equation, body length in centimeters, which we just figured out, times the safe swimming velocity, which is body length per second, equals the proper tank velocity. We just solved for safe swimming velocity and body lengths. Now we can actually solve for the velocity. So 10 centimeters times 2.2 body lengths per centimeter is 22.4 centimeters per second. That's the velocity. 20 centimeters times 1.7 body lengths per second, again we just figured this out in the previous equation, equals 34 centimeters per second. And on the 30 centimeter fish, 1.5 body lengths per second equals 45 centimeters per second. So you can kind of see the trend, and when you do more and more, you definitely see a trend. The bigger the fish, the lower the actual body lengths per second is going to be, but the faster the velocity is going to be. So you can tell as these fish grow, and according to their body length, they don't have to swim quite so fast, but they're still swimming much faster than the smaller fish. These velocities give us the desired speed at which we want to rotate the water in that culture vessel. And that's for proper muscle development, for overall fish health, and while maintaining the tank's self-cleaning properties for fast waste removal. Okay, so not only are we creating the velocities that are pulling waste out of that culture vessel fast, leaving us with optimum water quality for the fish, we're actually building their muscles. We're creating muscle development and working those fish out, which helps to get them to eat more, to get them to grow faster. Calculating the maximum feed rate is critical to designing several components of the recirculating aquaculture system. So we're moving on now to calculating the maximum feed rate. Feed ratios vary throughout the life cycle and they depend on what species you're actually growing. They can be upwards of 7% of the body weight per day as a small fry, newly hatched fry. So they're eating a lot during that initial development stage. And then it can be as low as 1% as a mature adult, say a mature trout, something like that, 1% of their body weight per day. 1 to 1.5% body weight per day is a good overall number to use in your calculations when raising fish to maturity. So if you're using calculations to figure out how much feed we're going to need to feed that tank, these are good numbers to plug in for the calculation unless you know something more specific. Do an example here really quick. We want to harvest 10,000 pounds of fish, which is 4,535 kilograms per year out of a single tank recirculating aquaculture system. And let's assume it takes 1 year to grow these fish out. So we're not growing two different harvests per year. 1 year to grow out in one tank. 10,000 pounds, 4,500 kilograms per year. For this example, we're going to use tilapia and assume that at the harvest size that we pull them out, they're eating 1.5% of their body weight per day. So 10,000 pounds times 1.5% gives us 150 pounds of food per day at harvest time. So when we pull those fish out, we're feeding the system 150 pounds of food a day. Okay, that gives us our total feed. We know off of that feed how much ammonia is going to be produced, which we're getting ready to talk about. what size mechanical filtration we need, how to size the flow rates, how to size the biofiltration. So that is key. And before, feed, again, the number one issue, how many pounds of fish do you want to raise per year? You need to figure that out, and that comes down to your business plan and what size operation you're actually planning on building. But when we know how many fish we want to raise, we can say how much food they're actually going to eat. And when we get to the aquaponics side of things, we're going to be able to relate this to plant growing area. So if you know you want to grow 1 acre of plant growing area, you can relate that back to how much feed it will take, and that feed will relate back to how many pounds of fish you actually need to design the fish culture system to produce. So everything's connected, and I hope that's fairly easy to see at this point. So calculating TAN. TAN is the total ammonia nitrogen produced from feeding the fish. So as we talked about earlier, as the fish eat the food, they excrete ammonia from their gills and in their waste product. Dependent on the protein content in the feed. So how much ammonia is produced is completely dependent on how much protein is in the feed that the fish is eating. Feed protein times 0.092 equals the amount of TAN per pound of feed. So equals X pounds of TAN per pound of feed. That's a fairly easy equation. We're just multiplying two numbers together and it gives us the TAN. So here's an example with 42% protein. We have 0.42 times 0.092, which is our constant, equals 0.0386 pounds of TAN per pound of feed, for every pound of feed. Or again, for every, this ends up being 17.5 grams of TAN for every kilogram of feed. If we have 10 pounds of feed per day going into the system, we just multiply that by 10. So that equals 0.386 pounds of TAN per day, or 175 grams of TAN per day. It's a fairly easy calculation. Now we know the waste product created per day. We're getting into it, folks. This is exactly what you need to know to get through these designs. More conservative calculation is below, okay? This is kind of a quick way to get there, and it leaves you with a little bit of a safety factor built in. So we assume 10% of the protein content in the food becomes TAN. So 10 pounds of feed, or 4.5 kilograms, at 42% protein would be 0.42, so that's the 42%, times 0.10 times 10 pounds. So times 10% times 10 pounds. That ends up equaling 0.42 pounds, or 190 grams of TAN per day. So as you can see, there's a small safety factor built in. 190 grams versus 175 grams, which is your actual number. And there's 15 grams more. So you would oversize your filtration a little bit, which doesn't hurt you as long as it's not an extreme amount. Okay, so now we have an example. And in this example, we're going to say that we have 1,000 pounds of fish that are being fed 1% of their body weight per day, and the fish food is a 32% protein feed. So maybe something like tilapia. We want to calculate the total ammonia nitrogen coming from that feed. So we do 1,000 pounds times 0.01, so times 1%, equals 10 pounds of feed per day. All right, so 1% of their body weight, we've got 10 pounds of feed per day going into this system. Then we have 0.32% protein times 0.10 times 10 pounds gives us 0.32 pounds of TAN per day generated from that 10 pounds of food at 32% protein. So on average, 30% of the proteins when we feed the fish remain in the fish's body for development. So they retain that in the muscle tissue, they use it for muscle and bone development. 70% of that nitrogen is actually lost into the environment, into the culture tank, and that's through their gills and through their waste product. So 15% exits as solids, while 55% is excreted as ammonia through the gills. Through the gills and other soft solids, we'll say, that rapidly degrade in the tank. Of that 15% solids, roughly 6% is going to end up degrading by the time we get the rest pulled out of the tank, while 9% is removed by our mechanical filtration. Now that definitely depends on what kind of mechanical filtration you have. If you have horrible mechanical filtration, you might get 1%. And if you have 20 to 30 micron drum screen filter, which is the other end of the spectrum, you might capture 12%. You might really get close to the total percentage of solids. And it also depends on your flow rate, how fast you're getting the solids into that filter before they're allowed to break down in the water column. So, having said that, this leaves us with roughly 61% of the nitrogen introduced by the feed to process through biofiltration, because that's in the water column. Now that we have calculated the daily feed rate and the TAN production, we can design the rest of the system. We can design the mechanical filtration because we know what the system flow rates will be in the culture tank, and we also know what the daily feed amount's going to be, so how much solids we're going to need to remove per day. The biofiltration, we can go ahead and size that. Again, we know the total ammonia and nitrogen production. We can use that to size the biofiltration and the flow rate. The water flow rates, just mentioned that, so the water flow rates for the whole system to go ahead and make sure that we have sufficient water quality for the species that we're rearing in the culture tanks. Aeration or oxygenation requirements. So now that we know how much food we're feeding and we know what the biofiltration is going to require, we can size aeration and oxygen requirements for the entire system. We can predict the waste accumulation, okay? It's going to be 7 to 15% of the feed weight. So if we feed 1,000 pounds of food a day, you're going to get 100 to 150 pounds of solid waste per day coming out of that system from your mechanical filtration. For aquaponics, we can predict the plant growing area and production volume based off of the feed rates. So this is all great, and the total ammonia and nitrogen will help us forecast how much nitrogen is going to be in the system. Filtration that removes solids by mechanical means, okay? This is mechanical filtration. We've talked a little bit about this. This is often done in several steps, but we will always want to remove the largest particles first. Get them out of the water as soon as possible, and then the finer solids can be removed afterwards. But with anything, as soon as the solids are out of the fish, we want them to the center bottom drain as quickly as possible and out of the system so that they're not breaking down in the culture tank. When we're looking at aquaponics, we can break them down elsewhere and add them into the plant portion. But if we have a species where that's going to take the water quality out of the specifications for the fish, say Arctic char or something like that, then we need to remove that as quickly as possible, break it down, and move it into the plants portion in a decoupled type system. So there are several different types of mechanical filters on the market, and we're going to talk about several in the equipment specification area. I'll just mention them here, and we're also going to show you how to DIY some of the filtration. Specifically, our radial flow filters and coldness upflow filters. So mechanical filtration, we have swirl filters. So they work by injecting the water at an angle, swirling the water, and concentrating the solids in the center. We have radial flow filters. They create a radial flow within the chamber. It allows you for a smaller vessel because the the residence time in that vessel is actually shorter to still pull out solids. So that is actually an upgrade in filtration from swirl filters. We have a baffled clarifier like the University of Virgin Islands built and used in their system for, again, 20 plus years. We have upflow media filters. It could be coldness upflow filter. It could be with some other type of filter media. We have pressurized bead filters. So that's a bank of beads, a bed of beads under pressure, and we inject the water in from underneath and allow it to travel up through that bed of beads, capturing the solids. We have micro screen drum filters, which capture, it's probably the standard in large scale commercial recirculating aquaculture. And it basically is a large screen that captures the solids. And as the solids begin to fill it up, the screen rotates and deposits the solids into a waste channel. And we'll talk about that more later. And then we have a belt screen filter, which isn't seen quite as often, but is also used to separate and concentrate the solids from the culture water. So here's a picture of a beautiful installation, and you can see a micro screen drum filter right here, where all of the water is collected, sent into the drum screen filter. The solids are filtered out and go out of the waste port, which goes out of this PVC line to wherever you're actually transporting the waste to. And then the clarified water goes through onto the rest of the system. Biological filtration. Now, we've talked about this a little bit in the Aquaponics 101. This is the nitrification is the process that converts harmful ammonia into relatively harmless nitrate nitrogen by way of the nitrogen cycle. So nitrous ammonius, NH, is actually going to take NH4 plus 1.5 molecules of oxygen, and it's going to yield 2 molecules of hydrogen, 1 molecule of H2O, water, and 1 molecule of NO2 negative, which is your nitrite. Nitrobacter, a separate type of nitrifying bacteria, is going to take in that nitrite and add 0.5 oxygen molecules. Through the process of consuming this, it adds 0.5 molecules of oxygen and creates NO3, okay, which is nitrate. That is our end product and the nitrogen product that we want for plants. It's easiest for them to take up into their system, and it's the least harmful of ammonia, nitrite, and nitrate to our fish culture or species that we're culturing. We want to keep the dissolved oxygen, DO, so you're going to see that abbreviated as DO throughout this course. We want to keep the dissolved oxygen above 4 milligrams per liter and preferably saturated. We want to keep that at saturation. Nitrifying bacteria require a feeding minimum of 0.07 milligrams per liter of ammonia and nitrite respectively for your Nitrobacter to stay active, to keep growing. If we don't have a feed source for the bacteria, they start to die off. The preferred alkalinity for the recirculating aquaculture system is a minimum of 100 milligrams per liter as calcium carbonate. So we'll talk a little bit more about alkalinity when we go through water quality, but that is the amount of calcium and buffering capacity within the system. Nitrification consumes alkalinity. So in order for your bacteria to consume ammonia and convert it to nitrite, to consume nitrite and convert it to nitrate, your nitrifying bacteria are going to consume alkalinity in the process. That's part of the process for them to carry out that reaction. Because of this, alkalinity needs to be maintained in a recirculating aquaculture system using sodium bicarbonate, which is baking soda, at 25% of the daily feed volume. So for example, if we're feeding 100 pounds of food a day, we actually have to feed the biofilter 25 pounds of sodium bicarbonate per day to keep up with the amount of ammonia that it's ammonia and nitrite that they're nitrifying and producing to their end product, that they're actually taking care of. So again, 25%. And that seems like a lot to people. 25 pounds of sodium bicarb at a time. Wow. Well, it is. And that is basically just a function of the biological reaction. So that's very normal. For every gram of NH4 that is oxidized to NO3 through nitrification, 7.14 grams of alkalinity are used. So we can calculate how much alkalinity is going to be used. 8.59 grams of carbonic acid are produced. So CO2 is produced in the biofilter. And like we talked about earlier, that's one of the byproducts that we're going to need to off-gas in a pure oxygen high density situation. 4.57 grams of oxygen are consumed. So the biofilter consumes oxygen just as your fish culture tank consumes oxygen. And that's a calculation that we are going to have to make to add into our total oxygen demand for the entire system. 0.21 grams of nitrifying bacterial cell mass is created. So cell mass is created, solids are created through this process. So you're going to get solids coming out of your biofilter. It's just a process of constantly growing bacteria and constantly having bacteria die off, cell mass die off. Some types of biological filtration that we will get into sizing and in the details on a little bit later when we go through equipment sizing are first off is moving bed bioreactor. So you'll see that abbreviated as an MBBR. And that's basically a large aerated moving bed of biological film carriers, pieces of plastic. And those are all moving in a bed. The nitrifying bacteria are fixed and attached to that media, and they consume and process the ammonia byproducts. We have a trickling filter that works from a pump pumping up to a height and then allowing gravity to trickle the water down through a plastic type media, where again we have fixed nitrifying bacteria processing that ammonia byproduct. We have a fluidized sand filter, which is the most efficient for square footage method that we have for biofiltration at this time. And that works by having a large sand bed that we inject water into the bottom at a flow rate that actually expands the sand and fluidizes it. So instead of being, say, 5 feet tall, once we inject water, it's 10 feet tall. And there's a tiny space around each granule of sand in that filter. Well, because of the space and the area for surface area for bacteria to attach to and grow, it is extremely efficient at processing ammonia. And we'll get into that a little bit later. It all comes down to the price of the filter, the efficiency that it can produce and process ammonia and nitrite, and the footprint that it takes up. And then again, last, the usability. How hard is it to maintain this filter? Do you build it, start it up, and never look at it again? Or are you doing daily maintenance to maintain that filter? Though biofilter media can look seemingly expensive, it is actually a low overall percentage of the total recirculating aquaculture system design, and it's imperative to proper system functionality. This would be like designing a house without a toilet and locking everybody in it for a year until you let them come back out. It doesn't work. You need a proper biofiltration package to make onshore recirculating aquaculture make it work. So keep this in mind. This is very, very important. It's the life support. Now we're going to move over to chemical filtration really quick. And chemical filtration is used to destroy pathogens, bacteria, algae, other organisms that are unwanted, and bring optimum water clarity in your culture water. So with UV, with ozone generators, or even with hydrogen peroxide at a correct dosage and usage, you can bring water that looks very turbid and brown to gin clear, crystal clear river looking water. So it's amazing what you can actually do by using UV, ozone, and hydrogen peroxide in a recirculating aquaculture system. And that's how, as you saw some of the slides earlier in the recirculating aquaculture pictures, you can see right through the water, you can see the bottom drain, you see the entire fish mass in the tank. And some of those tanks are very deep. So the reason is because they're using mechanical filtration and biological filtration optimally, and then they're further treating that to remove any kind of color or undesirable organisms from the water. And these can be a little bit different when we apply them to aquaponics, but we'll talk about all of that a little bit later. Water pumps. So there's many different types and brands of water pumps out there. All the way from calling up one pump manufacturer, they may manufacture 50 to 60 different types of pumps. If you go into a hardware store, you're going to get another line of pumps. So not all pumps are created equal. And it's very important to use the type and brand name of pump that's going to do the job you want efficiently, and that's actually going to last for your operation. So we're looking for maximum efficiency at the desired head height. Head height is the vertical lift. So if we want to pump water 10 feet from a tank in the ground up, straight up vertically, that's 10 feet of vertical head height. You'll see me refer to head height throughout the rest of this lecture. So we're looking for maximum efficiency at desired head height and water flow. Centrifugal pumps are very often used. That's what we use here at Chatterson Farms on our scale. Axial flow pumps are usually used in a larger commercial recirculating aquaculture system. And then we have magnetic drive pumps that can be used for smaller scale hobby type systems. Very common, they use a magnetic impeller to drive that water. And we'll talk about all these when we go through sizing water pumps and equipment selection later on. So here you'll see a water pump installation. You have 3 separate centrifugal water pumps, and then you've got a 4th centrifugal pump running some smaller sideline. And that's just a very typical multi-pump installation for a larger recirculating system. And that's it for this session. Again, if you have any questions at all, please email me, ryan@collegeofaquaponics.com, and I will be sure to cover those questions in our weekly question and answer session and make sure you get all the information that you need. Thank you very much.